Welcome. In this video, we're going to determine whether or not this series converges using the integral test. So before we can actually even begin on the integral test, we need to establish three things. The first is, well, do we have a continuous function? And that is, in our case, our function f of x is equal to 1 over x squared plus 4. Where the domain here, well, these are just integers, positive integers. So is f of x continuous? Secondly, we need to establish that f is positive. And finally, whether f of x is decreasing. Well, first, let's look at continuity. The only place where this function could be discontinuous is here in the denominator. Whenever x squared plus 4 will equal 0, this function will be discontinuous. But if you notice, this leaves us with x squared is equal to negative 2, and this you can't solve over the real. So this function's always continuous. Next, let's see if this function is positive. So for that, let's look at the different parts of it, the numerator and the denominator. So our numerator of 1, well, 1 is certainly positive. It's always greater than 0. What about x squared plus 4? Well, again, this is also greater than 0 since this is actually just a parabola shifted up 4 units. Now, since we have a positive numerator and a positive denominator, the result is also positive. Finally, we need to determine whether this function is decreasing or increasing. We need it to be decreasing, in fact. And an easy way to do that is just through Calc 1. So what is this derivative? That is f prime of x. Well, that's equal to negative 2x divided by x squared plus 4 squared. Now we need to ask ourselves, how can we use this derivative here? Well, remember, we only need to look at values that begin at 1 and go out to infinity. So on 1 to infinity on this interval, f prime of x will always be less than 0. Now, why is that? This denominator will always be positive. If I put in a 1, a 10, a 20, no matter what value I put in, I'm going to get that value squared plus 4 and then squared again. So this will always be positive. Now, what about the numerator? Well, our numerator, and again, I'm only looking at numbers from 1 to infinity. This will always be negative. If I put in 1, 10, 20, 100, we'll always get that number times negative 2, which makes it negative. And so again, this is on this interval. Well, actually, maybe I should rewrite this sentence so it makes a little bit more sense. And what I mean is, let's write it here. Since this denominator of x squared plus 4 squared is greater than 0, and since negative 2x is less than 0, on x between 1 and infinity, so let me update this a little bit, on x such that x lives inside here, so it follows that f prime of x is less than 0. Hence, f of x is decreasing. Okay, so now we've established that this function is continuous, positive, and decreasing. So now we can apply the integral test. And to apply the integral test, let's evaluate the integral from 1 to infinity of 1 over x squared plus 4 dx. So we need to rewrite this first as the limit as t approaches infinity of the integral from 1 to t of dx over x squared plus 4. Now, integrating, let's not forget our limit notation first. We end up with the limit of 1/2 tangent inverse of x over 2, and that's from 1 to t. And in case you have forgotten, I'll put this in as a little aside. That the integral of 1 over x squared plus a squared dx is equal to 1 over a times tangent inverse of x over a. If you don't have this memorized, or at least know where to write it down, somewhere you can reference it, please do that now. Now I can go ahead and evaluate this here, the antiderivative at the endpoints. Notice throughout I've kept my limit notation. I'm not using this right now. It's basically like something I'm ignoring, but I still need to evaluate these endpoints. And I still need my limit notation, so this is, I'm going to make this a little easier to write by bringing the constant of 1/2 out front and leaving me with tangent inverse of t over 2 minus tangent inverse of 1/2. Now this is where you need to dust off your trig thinking caps here, what you remember from trig. This here is just a constant. What I mean by this here, I should actually point to it. This is constant. This is some number. So I'm going to bring this out to the front. So this becomes 1/2 times, well, negative 1/2 times tangent inverse of 1/2 plus 1/2. The limit as t approaches infinity of tangent inverse of t over 2. So what is happening is t gets very large. This is what I said. Well, this is where I meant that you need your trig thinking caps. The graph of inverse tangent has a horizontal asymptote here at y equals pi over 2. Its graph looks like this on this side. And then on the other direction, it'll have the same a similar horizontal asymptote, y equals negative pi over 2. And now we're supposing that this is the t-axis. So as t grows out large, this curve of tangent inverse of x is going to approach pi over 2. So we're just left with negative tangent inverse of 1/2 over 2 plus pi over 2 times 1/2, which is just pi over 4. Now you can work this out on a calculator, but what